Good day, students. On this clip, we're going to be going over part one of the application of derivative series. We're going to be working on optimization here, part one of optimization, and we're going to be optimizing a fenced area. Okay. All right. So let's go ahead and take a look at the question. It says an archaeologist has 300 meters of fencing material to enclose a rectangular piece of land for excavation. What are the dimensions of the piece of land that will ensure that he encloses the maximum amount of area for excavation? All right. So if you read this problem, what are we maximizing here is the first thing you want to ask yourself. You're maximizing area. Okay. So the goal here is to find a formula for the area, a model for the area a of x in terms of just one variable. Okay. If I can find a formula for the area in terms of one variable, what I'm going to do is I'm going to uh, look for the critical point and the boundary point. Okay, so I'll test the upper and lower bound, and then I'll also test the critical uh, point. Okay, so let's say a of x is the as a function. Let's say we have f of x, a of x equals some function. So what we're going to do is find the boundaries for x. We're going to test the upper lower bound, and then we're also going to test the critical point, C, basically where a prime of x is equal to 0. Okay, so the ultimate goal again is to find a model for the area in terms of just one variable. All right, so that's the deal. Okay, so to help us come up with a formula for the area, we're going to have to give ourselves a visual about what's going on here. So we're enclosing a rectangular area, right, with a fencing material that's 300 meters long. So let's go ahead and draw the fencing material right here. So let's say this is the entire fencing material. It's 300 meters long, all right? So the length from here, we use a different approach. The length uh, from here all the way to here is 300 meters. Okay? All right, so what we're going to do is we're going to use that to create a rectangular region. All right, so what is that going to look like? Let's make a sketch of a rectangular region. I'm not going to draw it to scale. So let's say we just have a rectangle like this. Okay, so let's go ahead and label our rectangle. Now the goal again was to So the goal again is to create a model for the area using just one variable, okay? So we know that what is the formula for the area of a rectangle? The area of a rectangle is given by length times width, okay? So let's call this the width and let's call that the length, all right? So how about we set the width to x, all right? If the width is x, that means the bottom and the top will measure x, okay? So we have the width uh, of the fence used up, what portion of this fence is left to construct the length? That's the question, okay? So let's say we have the width on the top and the bottom. So let's say we have 1, 2, 3, 4, 5, 6. Let's say this portion is x. This accounts for just the bottom, okay? And then another 1, 2, 3, 4, 5, 6 accounts for the top, okay? So what we have now is we have taken out 2x from the entire fencing material that we have, okay? So we have taken out 2x, what do we have left? What we have left is simply um, the entire length, which is 300, minus what we took out, which is the top and the bottom, 2x, okay? All right, so this length has to be divided evenly amongst the L's, the sides of a rectangular region, because we know opposite sides of a rectangle are congruent, right? So what do we do here? We need to divide this remaining side, this remaining length, we need to divide it by 2, okay? So 1, 2, 3, 4, 5, 6, 7, 8. So 1, 2, 3, 4. Right down the center, that will be the length, that will be the first L right there, from there to there. Let me draw that again. Um, so from here to here will be the first L, and then from here to here will be the next L. Okay, but how do we figure out what these sides are? They're simply half of this entire length, right? So the entire length is 300 minus 2x. So this would be 300 minus 2x divided by 2. All right, so let's go ahead and indicate what our L is going to be. Our L is going to be 300 minus 2x over 2. That will be for this one side right here. 300 minus 2x over 2. And then the second length will be the same thing. 300 minus 2x over 2. Okay, that will be this side over here. 300 minus 2x over 2. Have we accomplished our goal? Absolutely, because right now the dimensions of my rectangle are just in terms of x. So A equals LW. I can write this now as a function of x, which was the initial goal. So A of x is equal to L, which is 300 minus 2x over 2. That's L times the width, which is just x. Okay? So this is the model that we're going to be optimizing. So let's simplify this a little bit so we can write this as A of x equals half of 300x minus 2x squared. What are the boundaries for x? Now, if we want to make the width as wide as possible, then we have nothing left for the length, right? So we're going to have, let me do this in green, twice 2x equals the entire length, which is 300. Okay? I hope this makes sense. Well, let me explain it in a different way. So we know that the perimeter 300 is basically made up of a width and a width and a length and a length. If we allocate absolutely nothing to the length to see how big the width can become, these two go away. The width is going to become x plus x. So we have 2x being equal to 300. In that case, the length is going to be 0. All right, so that tells me the widest this can possibly be. So you have 2x equals 0, so this would tell me the biggest value of x divided both sides by 2. So x is going to be bounded above by 150. So this is going to be the upper bound, okay? So how small can x become? X can be as small as nothing, right? In that case, the length would take the entire unit of measurement, all right? So x max is 150, and the smallest that x can be is 0, all right? So we need to include the boundaries for x here because we need to test them when checking for the max and min, okay? So this is the formula for the area, and x goes from either nothing all the way to 150. In that case, we're splitting it between the top and the bottom. Okay, you gotta be careful. It's not. This is not 300. All right, if you use 300, it's wrong because you're assuming you don't have a topper part for your rectangle, and that's not a rectangle. That's just a line. All right. Okay, so here we have it. So it's not that complicated anymore. So what we're gonna do is we're gonna find the critical value for this, and then we're going to test the boundary point and the critical value. Whatever yields the highest output will give us will be the correct measurement for the width, and then we'll also go ahead and find the measurement for the length. All right. So how do we find a critical value? Critical value happens when the first derivative is 0. So we're going to find what the x value that satisfies this equation, right? So let's go ahead and find that. The c, that's what c is. So we're going to differentiate this area of function right here. So it's going to be factor out the 1/2. The derivative of 300x is 300 minus 4x. Okay? Okay, now we need to set this equation to 0. So we have 1/2 times 300 minus 4x equals 0. Multiply both sides by 2. We have 300 minus 4x equals 0. So, and then we have negative 4x equals negative 300. And when you divide by negative 4, you end up with x equals 75 meters. Okay? So, all right, so let's go ahead and test each one of them. All right, so we know that a of x equals 1/2 times 300 300x minus 2x squared. All right? So if you can do this with your calculator. If you plug in a of 0, you're going to find out that is exactly equal to a of 150. And that is a scenario where you're enclosing 0 area. Okay? And then you can test, obviously, a of 75. You can plug that in your calculator. So a of 75 is going to be 5,625 square meters. All right, so this is clearly much bigger than these two. This is absolutely nothing. All right, so x equals 75 gives us the biggest area. It tells us the width of the biggest area. So what is the length? That's the next question. What's the length going to be? Um, we know that we had the length explicitly defined in terms of the width x as 300 minus 2x over 2. So L is 300 minus 2x over 2. Okay? So we're going to plug in 75 for x. So that's going to give us 300 minus 2 times 75 over 2. Remember, this is w, okay? Because x is w, we defined that earlier. So this becomes, let's see, 300 minus 150 over 2. 150, 300 minus 150 is 150 over 2 is 75 meters. Okay? So the length is 75 meters and the width is 75 meters. So basically we see that it's a square that encloses the maximum area, okay? So the dimension of uh, the dimension of the rectangle um, that rectangle piece of land, or however we're going to call it, the dimension of the rectangle that encloses the maximum amount of area is 75 meters by 75 meters, which is basically a square. All right, so there you have it. So thanks so much for taking the time to watch this presentation. Feel free to subscribe to my channel by clicking up here. And if you like this video, you can always click like. And please, please, please post a comment down here to tell me what you think in the comment section. I really appreciate it. More videos coming from themarketerserve.com. Thanks again and have a wonderful day.